Okay, good morning, guys. All right. Oh, okay. All right. So you sound quiet. Okay. Okay. Let me check. Uh, actually, I haven't done anything to the setting. Okay. Let me try. Oh, maybe wrong device again. Oh, it's correct. So is it better? Nope, doesn't. Yeah. Oh, okay. I haven't changed anything. Or maybe just microphone is a little bit far away. Okay. All right. So just let me know if at any time the sound was just, I don't know, disappear or just getting sort of fading out. All right, guys. So we're gonna have a lot of fun again today. I've been trying to say that like every time. But I hope you're having fun with the physics. Oh, fun, yeah. All right. So we have come so far to the position that we are able to do the full analysis of something that is really close to the realistic device or an engine or an equipment or whatever that runs using thermal driven properties or whatever, something that's run by temperature differences. All right. So that's what we are trying to get to today. And this is the main diagram that we discussed toward the end of last lecture, that humans trying to steal, I'm using the word steal, but I'm not sure is that the right word or not. But it means it's like, because now we know that there is an energy flow from hot to cold that's natural. So is it possible that because of that flow is the energy flow, is it possible that we can redirect part of it? Or if it would be better if we can redirect everything and then use those energies to do something useful, and that we name those useful energy to be doing some work. Okay. And we sort of like, it was like a spoiler already. So I just told you guys that that's not possible for you to redirect 100% of that heat flow and turn them into something useful. No, you have some efficiency, right? You only have like a partial ability to do that. So that's why we define the word efficiency. So it's the ability that you can extract part of the provided energy and use that to do something useful. And what about the rest? You have to throw them away. You cannot keep it, right? Too bad. So that means if you provide some use, I mean, not useful, sorry. If you provide some energy under like a hot temperature, hot reservoir up here, that's the Q hot, something that flow from the hot reservoir. And then because you only use some of it, so that means part of it, you're gonna have to discard it out. So you have to dump them out down here in the cold reservoir. Okay, so there is a difference between the incoming and an outgoing. Those difference from the conservation of energy, that is going to turn into a useful work right there. You guys with me? So that's everything is first law of thermodynamics. It's all about conservation of energy. So when you can extract, I mean, there is a flow, heat flow in Q hot, and part of it you have to dump out Q cold. The difference has to be the work done. Okay, that's conservation of energy. But because we would like to do the calculation on the efficiency, how efficient is this machine doing the work? So you divide with that Q hot that you provide in the first place. You guys with me? All right. So once you divide that ratio, that is the efficiency of that device. Okay. And the device that run by the thermal difference, we name it the thermal engine. It's the engine that run thermally using thermal properties to run. And that's why we have the heat engine right here. That's our main engines or device that we are about to discuss right now. Okay, guys, with me? So I think this is going to be the main equation describing the efficiency of an engine. This is it. All right. So what you get over what you have to provide, that is just the key concepts of the efficiency in general. All right. Like example last time that I showed you guys, I mean talked about it. I teach 2 hours. How many minutes that you sort of get the material from this lecture? That's the efficiency already, right? Okay, let's look at the quick example right here. So now we do some calculation. All right. You have a gas engine, burns 0.2 gram of fuel and delivers 2000 joule of work per cycle. So does that make sense? So this is what happened in your car engine. So you burn some oil, some gas and all this stuff, and then you get some energy from that chemical energy stored in the gas. Given that the heat of combustion, that's the heat that you get after you combust a gas. You have the heat of combustion equal to 5 times 10 to the fourth joule per gram. So this means every gram of gas that you burn, you will acquire 5 times 10 to the fourth joule. Okay, cool. All right, find the heat discarded in each cycle and the thermal efficiency of the engine. All right, so that's good. So first of all, you have only 0.2 gram to burn. And each gram, you get this much of energy. So how much energy you actually get from the combustion? So that's a Q equal to the mass that you're going to burn times the amount of the heat of combustion. So when you look at this equation, it looks like the latent heat, right? But that is just a general way of writing like a product between the amount of mass times something per unit mass. That's what it is. All right. So this is what you get. So you have 0.2 gram. Don't need to convert any units because the heat of combustion is already per gram. So it's 5 times 10 to the fourth joule per gram. Perfect. So that is what? 10,000 joules. All right. So at least now you know once you burn this 0.2 gram of gas, you get this much energy. And this is the part that I'm going to call it Q hot. You guys with me? Because when you burn it, you get energy that is equivalent to the hot reservoir right here. So now I hope you see the way that you can start to provide the engine with the hot reservoir. It doesn't have to be like a big reservoir or anything, but at least you can gain some huge energy through like this chemical interactions or chemical reaction or something like that. All right, so this is the Q hot that we have been talking about. All right, now it turns out the amount of work that you can get every time that you burn this. And then one thing that you can sort of notice right here, each cycle, because you want to run this thing repetitively, you want to go again, again, and again, and again. So now you start to see that eventually the engine has to run in cycle. And that's what the cylinder and everything in your car engine is behaving, is just go back and forth, back and forth. So every cycle you're doing this thing, every cycle you're doing this thing. So that's why every cycle you burn 0.2 gram of heat, you gain 10,000 joules and you deliver 2,000 joules of work. So where's the rest? You have to throw them away. And that is the Q cold. You guys with me? All right. Even though the name is cold, but well, you know, it's not that cold. All right. That's it. From the conservation of energy, the rest go to the discarded heat. And that is just 10,000. Subtract out 2,000. And that is 8,000 joule. All right. So what is the efficiency of the engine, guys? Well, okay, no big deal. What you get 2,000 joule. What you have to provide, you provide 10,000 joule. So the efficiency of this one is only 0.2, or you can say 20% efficient. Done. All right. So I hope this summarized the concepts of the efficiency and the main diagram. What does it mean when you're looking at the heat, the Q hot, the heat that you draw into the engine, and some part of the heat has to be discarded out to the environment or whatever is supposed to be like colder. And then the difference between the two cannot go anywhere except just the work done by the engine. Okay, cool. All right. But the number is not that bad. When you look at this one, you might say, well, John, this is like low efficiency engine. But in real engine, actually, the car engine, when you run like a diesel or like, I don't know, gas or haul or whatever, I think your efficiency can go up to only like maybe 45% or so. Maybe diesel can go like 40 something, but I don't even think that it can reach like 50%. So that what does it mean? It means every gas that you combust in the engine, half of those energy get thrown away. And that's why the front of your car is really hot when you're running it. That's the the front of your car is really heated up. That because of that discarded heat. Sounds good? All right. And now you can see that every time that you run your car, you throw away half of your energy away. Why electricity is more efficient? Okay, that's a good question. So this is the reason why we are moving toward the electric car, because in the electric car, you are not relying on the thermal properties. So what you relying on is you turn the chemical reactions in the maybe lithium ions, and then you run the motor directly. So is a motor that get the energy. Once the motor runs, and actually motor is a very high efficient device. Once it runs and it's keep running, then you can get the efficiency up to maybe like 90-95% on and on. So that's why using electric car is going to be much more efficient. All right. However, you have to take into account the efficiency during the process of the battery itself on and on. So that's why I think effectively, in terms of like from the source of the energy down to the final running car, running electric car, I think the efficiency can go up to maybe 80 or something percent. Yeah. So electric car is better overall because of the, I will give it to the, I give it to the motor. The motor is really very highly efficient device. Yes. All right. And I think the battery is getting better and better. Right. Now you can see like a million miles battery and all this stuff by Tesla and all this stuff. So as long as you can do a rechargeable and the process is very reproducible with a very sort of like a small rate of deterioration, I think we are in good shape, right? We can get like 90% efficient car. So it's very possible now. I think they claim even higher than that, if I remember the numbers correctly. I think there's 90 something. But to me, I take into account the efficiency in processing the lithium ion itself. I don't know how efficient are they in producing like a battery pack. So that's, I don't know. All right. But in terms of once you get that battery pack, and if you put it into your electric car, the efficiency is 90 something. Yeah, that's good. All right. So I think we are pretty close to not using the natural gas or the natural sources for the fuel already. Well, but anyway, you still have to use nature's resources anyway. You have to figure out where are those lithium and all that stuff, and then you mine them. All right, but it's better. It's more efficient. All right, that's a very good question. Thank you for that. Okay. All right, so just on passing, because we mentioned about this last time. All right, if you want to run this in reverse, right? Remember we named it like heat pump because it's just like a water pump. Water goes from high to low. So if you want to take the water from low to high, you have to pump that water up. Same thing with the heat. Heat flow from hot to cold. If you want to bring heat from cold to hot, it's a heat pump. All right. But then if you want to call or you want to talk about the efficiency of heat pump, the example of heat pump, that's just the air conditioner that we are using like everywhere right now. For example, think about this just one more time. I want to explain this one more time just to make sure that you understand that the refrigerator is the heat engine running in reverse. This room right here that I'm in is under air conditions. So what I'm at right now is, let's say 25 degrees Celsius. But now outside, out of the windows and everywhere around this room, it's, let's say 35. It's hot. Let's say it's just regular normal temperature. So the air conditioner try to keep this room cool by taking away the heat from the inside room to the outside. You guys with me? All right. So that means this is in the room and this is outside. So that's why the air conditioner is trying to transfer the heat from the colder temperature place to a hotter, higher temperature place outside. Okay. And the way that this can run, all right, you have to plug it in. All right. So you have to provide the air conditioner with some energy to run the condenser, compressor, I mean, everything. That's what it is. All right. So that's what it is. Now, how are you going to measure the efficiency of air conditioner? Because right now, what you want is not the work done. You're not trying to lift things up. You want to cool this room down. So what you want to get is this right here, guys, is how much heat or how much energy can be pulled from the cold room to the outside, right? This is, you want to measure how good is this air conditioner. You just say, hey, how fast or maybe how much can you make this place cold? So this is what you are interested in, is the Q cold. But what you have to provide, you have to provide this. This is what you have to provide, the work. So by the concept of efficiency is the ratio between what you get over what you have to provide. So that's why is the Q cold right there. That's good. Divided by the provided energy, which is the W. That's it. All right. So the concept of efficiency is universal, except it's going to sound really weird if you have something that has efficiency larger than 1, because you gain more than you provide, which is weird. Like you put in 1, you get back 2. That's like efficiency of 2. That's this word is kind of, and it's kind of weird in itself. So that's why they're trying to avoid the word efficiency in this kind of scenario. So they have another name they call the coefficient of performance. All right. The reason is because this ratio can go larger than 1. So we just sort of like reserve the word efficiency for efficiency that runs between 0 and 1. That's what efficiency is supposed to be. The range of the efficiency has to be between 0 and 1. Okay. All right. And one more time. That's one twist. Even though, well, for us, because we care about cooling down the place. So that's why this is the coefficient of performance in the cooling mode, because we want to use this air conditioner as an air conditioner just to cool room down. But in a colder country, in the colder places, outside is snowing like crazy, you want to keep inside the house warm. That's the difference. So if that is the case, you are interested in this portion of the device. So you want to know if you want to take this device to act like a heater. So if that is the case, you are measuring the Q hot, because you want to know how hot can you make this room hot. I mean, how hot can you make this room? So that's what you want to measure. You want to gauge. You want to measure the amount of heat that you can pull into the room. So in that case, in the colder country and in the cold weather country, so what you are interested in is the hot part, and that's inside, and outside, that is snowing, that is outside. Why I say just inside, that means, sorry. All right, that's what it means. Okay, got it. So if that is the case, I mean, this is just comparison. So you might have a coefficient of performance in the heating modes, and that will be Q hot over W. I hope you get the concept. All right. But in Thailand, of course, we only care about the cooling mode. Plus, for the heating modes, well, you have other ways to make the room hot. You probably don't need a device or anything. You can burn like some wood, or you can, turn on the something very low efficient stuff like, I don't know, power supply, maybe the cheap power supply, or, I don't know what else. I don't know, doing some, turn something on, some electric stuff on. They will get hot by itself. All right. So there's a question comes in, do heat engine pump lose efficient in sound? Yeah, overall, in reality, yes, you have to take everything into account. So any vibration, any sound generated, but if you try to calculate, for example, the sound, the energy that carried away through sound wave is going to be very, very small in comparison to the amount of energy that you are trying to pump in and out. Make sense? All right. And vibration, for example, if you calculate the kinetic energy of that vibration, it will be like different order of magnitude than the heat that you're trying to pump from the room outside of whatever outside in and on and on. All right. So in general, that can be, I think, in at least to the first order, you can ignore those. Yeah. All right. But I mean, of course, in reality, you have to take into account every form of energy. Yes. Okay. All right. So I hope you see the whole grand picture of what is it about the heat engine. And now what we are trying to get to is this. Now that is the fun part. And what I am trying to get you to do is first, of course, apply the first law of thermodynamics. Second, know how to calculate the efficiency of an engine. But now the third one is I'm going to introduce to you the part of the second law of thermodynamics. And that would be crazy. Once you sort of understand this concept right here, you will be able to tell what is going to be the best thermal engine in this universe. All right. Tony Stark cannot do better than this as long as he want to use thermal engine, which he is not using that, I guess. He used some nanotech or I don't know, some weird nuclear, I don't know. All right. Now look at this slide right here. Look at the left and the right. We have seen this already once or twice. You have a wall that is insulated. All right. You have the gas in that tank. So you have a container with an insulated wall. And let's say the gas is initially is at the bottom half of this tank. It's being divided by a membrane. Okay, sounds good. But then suddenly somehow membrane just expires and it breaks. So the gas just fill up the whole space inside this container. All right. So we already know how to calculate this because it's a PV equal to nRT. So what you can do is like PI VI over TI equal to PF VF over TF, on and on. But then you already knew that, oh, Ajahn, the temperature will not change because you insulated everything. We learned about this one. There's no heat flow in and out. There's no work because it's not expandable. And that from the first law of thermodynamics, this process is nothing. It's a free expansion. It's just expand for free. You get nothing at all. So you know that the temperature will not change as well. See, so that's an application of the first law of thermodynamics. I think you start to see the connections. So that means the temperature can be canceled. So this one is easy, but John, the gas volume is twice as big, so the pressure will be reduced in half. So in terms of the property of gas, all right, no problem, you can calculate it. But one thing that is sure, this process cannot get reversed. It's impossible to go back. So I am introducing to you now another word, the reversibility of the process. So going backward, oh, my arrow looks really bad. Going backwards has nothing against the first law of thermodynamics. Can you see this? First law of thermodynamics still allow you to go backward because the energy after and before, they have exactly the same amount. However, I mean, by you can tell that's not possible, Dan. Well, I wouldn't say the word impossible. There might be a case, but you might argue, but Ajahn, wait. There might be a case that you wait long enough and there will be some accident that is just like all of those molecules suddenly decided to stay at the bottom half of the tank. Yes, there is a possibility there. But if you take into account the amount of molecules in this tank, it's going to be like a Avogadro number. To have those molecules with that big of numbers in harmony, collectively, like, hey guys, let's gather around at the bottom half of the tank. You can see, I mean, for those of you to do math, the possibility of that will be like longer than the age of the universe. So you wait until the end of the universe, you might not be able to see these events occur. Does that make sense? All right, so we will conclude that it's impossible. Okay. All right. Okay, forget about gravity for now. Talk about yeah, time machine, gravity is just later. Okay, that's not what it is yet. All right, but we'll discuss a lot more fun with the concept of this irreversibility and time. They are somehow related. Okay, anyway, so that's irreversibility come into the picture. But now look at the right-hand side. It's almost the same scenario. Okay, so you have a gas, initially the same volume, exact same volume as this, same. But then now you have a piston, a movable one that you can lower or raise this piston up and down. And in the bottom, you attach this one to the energy reservoir. So when you have energy reservoir, now everyone understands that what it means is you fix the temperature, right? Because we already saw that, or we already agreed that once you have like some big source of energy, you cannot change its energy easily. It's too big for you to do anything. So that means that's already forced you to have the gas in your container to have the same temperature as the energy reservoir. And this temperature will not change. So you already meet the same condition of no temperature change. When no temperature is being changed, that means your internal energy will not change either. Cool. But because you have a movable piston there, so you can actually do the work and there will be some heat flow. Okay, you guys with me? All right. And this one is good in the sense that if you start pouring the sand, this one is imagination. Don't forget that we are not doing this for real. All right. This is like a thought experiment. So this is just an experiment that you in your head. So you're pouring some sand in. So the weight of the sand will push down the piston slowly. So that means you're compressing the gas down a little bit. All right. So when you're compressing the gas down, the work done is going to be negative because volume is decreasing. When the W is negative, from the first law of thermodynamics, delta U equal to Q minus W. So that means in this process, whatever the work is being done is going to be exactly the same as the heat flow. So when you're pouring in the sand, the volume is reducing volume, W is negative. When it's going down, W is negative. That means heat is also negative. You guys with me? So far, so good? But the negative heat, what does it mean? It means heat leaves the system. So that's mean, think of it this way, is like when you compress this gas down a bit, you squeeze the heat out of the system a little bit. But that's not the point of this. All right. You already understood this process because this is an isothermal process. Temperature does not change. The internal energy does not change, right? But the concept of this that I want to talk about is the reversibility, guys. You say, well, Ajahn, I changed my mind. I want to pick up the sand one by one. All right. And once you do that, you can slowly lift things up. I mean, it's going to slowly lifting up because the weight that is pushing the piston down is getting smaller and smaller. So it's going to come up to the original position again. So in that case, it looks like you are trying to get to the process that is reversible. You guys with me? And this is the thought process that trying to talk about the word that we skipped. I don't know, you still remember that? But there is a word that you said that, okay, I'm going to talk about this later. It's a quasi-static process. When I say quasi-static process, it means it's sort of static, but it's not totally static because you want to still move things around. But you move it so slowly that at any point in time, it looks static. And you do not disturb the system too much. Does that make sense? It doesn't make sense, I know. But yeah, that's what it is. Yeah. So now you start to see, well, Ajahn, so what we have been studying is like in our imagination. The answer is yeah. Oh, I still have the music on. I suppose you just have like sound effect right here. Yeah. The reason is in reality, when you let the gas into a tank, it just flow, right? But you have to wait a little bit for the gas to pretty much disperse everywhere, and then you measure the pressure. But right at the moment of you let the gas into a tank, there'll be some part in the tank that doesn't have anything just yet. And there'll be some part of the tank that, hey, filled with like crazy gas is running around. So you just have to wait a little bit for, okay, the gas to disperse and everything is in equilibrium. And then you measure the temperature, the pressure, and everything. Does that make sense? So that's why whenever you have a PV diagram, and then you can draw some process on the PV diagram, that has to be done in a reversible way. That means for you to walk through those processes, you have to do it slowly enough. Because at each point, you should be able to measure the pressure and volume correctly. So you probably have to, hey, slowly, guys, just like, hey, just move a little bit. And then you don't have to move and stop, but at least the change has to go gradually enough for you to be able to measure the pressure and volume and temperature and everything quite at a good numbers that representing the whole system. Okay, sounds good. All right. But in reality, that's not what you do. So this is the reason why this is the weird conclusion of this slide. It turns out the process in this world, I use the word world, but I could say the universe, I think. I just want to leave some possibility there. All right. Every process is irreversible, guys. Seriously. Woo-hoo. Yeah. All right. You're getting older. It's not reversible. What else? You have a glass of water that's hot. You have hot coffee. You have it sit there. It's getting down to room temperature. It's not reversible. You cannot make the coffee hot again by itself, of course. I mean, you can warm it up using microwave and stuff, but I mean, by itself is not. You have an ice melt to the room temperature. You cannot reverse that process by itself. It's not possible. Yeah, you see? So every process that happens, those are irreversible. Yeah. All right. There are a couple comments there. Oh, just wait there. Hold it. All right, we'll get to it. All right. So why I'm talking about this for so long? It took me like 10, 15 minutes to talk about this. Guys, look at this. This is very crucial. And it might sound vague to you. It might sound sort of like unclear, but I mean, if you try to wrap your heads around it, it's going to make some sense. Okay, think about this. So now we are focusing on reversibility and irreversibility, okay? So over here, you have a metal box, quite hot, 70 degrees Celsius. You have an ice cube in there at 0 degree. Wait a little bit, ice melt, metal box cool down. You end up with the liquid water at 40 degrees Celsius. This is good, but you are sure this is definitely not reversible. Impossible for you to go back. With me? And during this process, there is a heat involved. You can calculate this using like MC delta T, ML, on and on. You are able to calculate the amount of heat that involved in this melting of the ice cube. Cool. This is good.
Okay.
Now look at the bottom case. You have a different kind of setup. You have a metal box, but sit right at the transition temperature, 0 degrees Celsius. And then you have an ice cube, same one. But then, of course, the ice cube is just like, hey, I'm not sure what to do because the metal box is already sitting at the same temperature. But due to the non-uniformity at the level of the Avogadro numbers, right? Because you cannot control million of the molecules to behave exactly the same. There will be some portion in time or whatever, some fraction or some in space or whatever that you might see yourself looking at a liquid water at 0 degree. But sometimes you go by that crazy stuff, all right, it's still solid, guys. But okay, you're not so sure because everything is already equilibrium at 0 degrees Celsius, is right at the transition temperature. So the best that you can say is this is still reversible process. Okay, so from the look of it, Ajahn, it seems like, well, the melting process that might occur at this temperature seems to be reversible because you cannot control it. It doesn't really go away. It still have a chance, or you don't really know what is going to happen, but it's sit right at 0 degrees Celsius. So you can say this is still reversible. But then you think about it, but the melting process also involves heat. And I mean, because this is, I mean, if you want to calculate this in ml, some transition latent heat, the heat during the transition phase, phase transition. So this is the heat involved, but it's involved in a reversible process. And this is what we are trying to get to, guys. The heat in the upper case is one way. Is one way. Is one way. It's one way. And whenever you have heat that runs in one way and then you cannot bring it back anymore, that means that heat pretty much lost forever. You will not be able to bring that energy back. You have no chance to make it useful anymore. Make sense?
Okay.
On the other hand, in the bottom case, you have heat involved, but this one is still with you because it's not going away. It's two directions, it's two ways. You can go forward and then you can still, hey, just take it back. So these still have a chance to do something useful later. So these two contrast scenario bring you to this. Think about the efficiency. When you have efficiency in an engine, you try to reduce the amount of heat discarded. When you say discarded, that means you trash it. It's out and it's gone. Okay. So whenever heat ends up right here, that is the lost heat, the heat that's gonna be lost forever from your system. And that's not good because from the efficiency, you try to minimize the Q cold as much as possible. The smaller this one gets, the bigger the Q hot will get. So that means having the heat, use the red one, heat in this scenario is going to impact negatively to your efficiency. You guys with me? You want to get the heat in this condition because that's the heat that is still useful for you later. And that's it, guys. Conclusion is this. Because you are trying to run a heat engine, okay?
Okay.
And then you try to draw the heat from the hot reservoir. You know that some of it you're going to get thrown away. I mean, it's going to get thrown away in the cold reservoir. So you still have to change the temperature. You still have to have the heat flow in and out. But then you say, the question that I'm going to try to answer is, what is going to be the highest efficiency that you can attain in the system? We just use this knowledge right here. Just say, okay, Dan, I cannot avoid it. So it means if you're going to transfer the heat, we are going to transfer it by not changing the temperature because we can see that not changing the temperature is good. Whatever that is going on in that scenario is still sort of not going away. So we're trying to use the isothermal process during the heat transfer step. With me? But then because you cannot avoid changing your temperature, so if you are going to change your temperature, you're trying to minimize the heat that is going to lost during that temperature. How you're going to minimize it? We're gonna block them all.
Okay.
So what we're gonna do is just, hey, okay, if you want to change the temperature, right, good. I am, oh, my microphone is down. That's why it's not so clear. So if you are at the point that you want to have to change your temperature, of course, I'm gonna not allow any heat to exchange because that heat exchange is gonna hurt my efficiency. So I'm gonna do it through adiabatic process. If you can combine the isothermal process and adiabatic process and build an engine that based on these two processes, you're gonna get the best engine in the universe. And that has a name. It's named Kernel Engine. All right. And that Kernel engine is going to be the engine that is going to be the best engine that can run between any two energy reservoirs. Other kind of engine is going to have lower performance. This is going to be the upper limit of the engine that run between two temperatures, the hot and the cold. There's a question comes in. So that's why I explained why the fridge has an insulator. Well, I think maybe that's not the real application of insulated air condition, the refrigerator. I think that's just to keep things cool, I guess. Yeah, but that might have some effect on this. But the things actually running is the compressor behind the refrigerator. That is your system. The coolant agent that runs inside your refrigerator, that's the one that doing the thermodynamics. Yeah. But the inside your fridge, that is just the one that keep things cold. So they want to insulate them because you don't want other heat flow into your fridge through other processes. I think that's what it is. All right. Oh, this one keep dropping. Okay, let me adjust this. All right. Okay. All right, guys. So now you sort of get introduced to the Kernel engine, and this is what it is. It looks like this. We already understood the whole thing. So let's start from this point A. Okay. So go with me a little bit, and it might sound a little weird first time seeing this, but that's what it is. So don't forget, every time that you look at a point in the PV diagram, it must be sitting on an isotherm. So let me draw an isotherm for point A. It's right there, right? But now, because let's say that you're starting from the point that you want to draw in the heat, okay? Because that's the upper, okay, let me draw the diagram on the side. So that's the upper half, the one you want to draw, that's hot, T hot. So I want to draw in the heat, that's a Q hot. So let's say we're starting from point A, and then that is a point when you want to draw in the heat. You want to sort of, hey, pull the heat into the system. But then we just said, every time that you have the heat transfer, we want to do it through isothermal process. You guys with me? So this is a reason why I just want to ride along an isotherm during this process. See, I am on that isotherm. I'm not stepping out from this isotherm. That's right there. And during this process, I am pulling down Q hot, which actually you can know how to calculate. If you remember from the isothermal process, the Q is just nRT log V final over V initial, but that's no big deal. You can do that calculation later. Now, once you arrive at point B, you want to do something. I mean, do something means to run engine, you have to run between hot and cold reservoir, right? So that means there must be some cold reservoir waiting for you to dump your heat out. Okay, but to do that, of course, you have to go to a different temperature. But then we just said, if you want to do it temperature change, you have to do it in an adiabatic process. So that means if I want to jump out from upper isotherm to a lower isotherm. So let's say I'm aiming for a lower isotherm, that is a lower temperature point I want to get to. I have to do it adiabatically. And if you guys do remember this one, remember adiabatic curve is the curve that is steeper than the isothermal line. Okay, so that's good. So that means during the expansion, if you want to expand the gas adiabatically, the curve will be steep right there. And that's give you a jump from a higher isotherm to a lower isotherm. So perfect. So that's going to be the jump that I'm wanting to do right there. Okay, so now you arrived at point C at lower temperature now. But then, of course, things has to run in cycle. So you have to aim back to get to A because you want to get things in full cycle, and then you want to repeat this whole process one more time. So this is a good chance for you to dump out your discarded heat. And once again, the requirement is every time that you want to transfer heat, you do it isothermally. See? So that's why from C to D, you are sitting on that isothermal line. You're not jumping out from this isotherm. All right. And during this process, you discard out that heat. Once you now arrive at point D, you want to run everything in full cycle. You want to have to jump back to a higher temperature. So you want to shoot things back to A. That is another temperature change. Every time that you want to change the temperature, you use adiabatic process. So I have another adiabatic to jump everything back to A, shoot things back adiabatically. And that completes the cycle. This is the Kernel cycle. And the engine that runs using this cycle, that is the Kernel engine.
Okay.
All right, guys, pretty good. And it turns out this is going to be your best engine in this universe that you are in. Other engines will run more poorly, cannot help. All right. And how good is this? It turns out I can prove it to you. And that would take me like 10 minutes or even 15 minutes more. And you guys hated it so much a few semester back. So I decided not to show you anymore. You guys didn't like that. But anyway, you had enough knowledge. If you want to crank through this slide, be happy to. But the key is I'm not using anything much. I'm just using the result that we already learned before, like this. You know how to calculate the heat involved during the isothermal process. You know how to deal with the adiabatic process using the PV to the gamma equal to constant. And then now you are having 4 equations. And then you can pretty much look at the relationship on and on. Good news. The end result is super nice. It's super, super nice.
Okay.
The end result is the ratio between the discarded heat, the Q cold, to the Q hot is exactly the same as the T cold over T hot. Isn't that nice? So that means once you are talking about the Kernel engine, you can use the original expression for the efficiency, and then you concentrate on that ratio right here. That ratio now can be turned to just a ratio of the temperature. And that is the best engine in the universe. Oh, that is too much. All right. But anyway, that's what it is. So what you have over here is now, if you have an engine that runs between two, if you know the highest temperature possible and lowest temperature that this engine is running, you will know the theoretical limit of the efficiency that an engine can get is the Kernel cycle. All right. And other type, other processes, other shape of the PV diagram processes will give you lower efficiency, 100%. 100% means all the time. Guarantee.
Okay.
All right. Sounds good. All right. I think this is a good point to take a break. And if you like, I'll just give you just a quick sort of like, we're not going through this because we are not trying to do like mechanical engineering or anything. So what we have over here is, this is an example that this one in like run in the gasoline engine. As you can see, the shape of the cycle that you run in your car engine, it doesn't look anything close to the Kernel engine, right? It has like an adiabatic process, constant volume, another adiabatic, and another constant volume. So if we calculate the efficiency of this cycle right here, it's going to be lower than the Kernel cycle. That's all. All right, but we are not going to go through the cycle that looks this complicated. We're going to look at something that's much more simpler. I mean, the shape of the cycle is going to be easier to do. Okay, sounds good? All right, so let's take a break right here, and then we'll come back and we're really going to dive into a real calculation right here. But this is like pretty much the highlight of applications of first law of thermodynamics is right here. All right. Okay, guys, let's take 10 minutes and we'll back with more exciting stuff. Okay, let's start with this example right here. You have 3 engines operate between reservoirs separated in temperature by 300 K. The reservoir temperatures are as follows. You have the engine A running between 1000 and 700 K, engine B between 800 and 500 K, engine Z is from 600 to 300 K. You think which one has the highest efficiency? You guys are kind of quiet today. Which one you think has the highest efficiency? And now, by answering this, I think you have an idea how to answer the question why we cannot charge your smartphone using your body temperature. I think. Any body? All right, all right, all right. I'll do it. All right. Oh, it's ABC. Order, ranking. Okay, very good. So that's the A has the highest and down to the C. Okay. And another person say, okay, Thanapon say engine C is the highest. All right. Okay, here's the key. Because now we know that the upper limit of an engine that can run between any two temperatures is limited by that Kernel efficiency. So let me put subscript C for that is the E sub C, and is a 1 minus T cold over T hot, right? You replace the ratio between the heat discarded and the heat hot, Q hot, the heat that get into the system by the ratio of the temperature. So as you can see, I mean, actually what you can do, you just calculate these ratio out. But my extreme example is this. What happens if you running the difference of 300 Kelvin between 1 million and 1 million plus 300? You see my point right here? So that means if you are in some crazy store that is super, super hot, like 1 million Kelvin hot, and then you try to run the engine that actually 300 Kelvin higher than that surface temperature of that star, your temperature of the cold part will be 1 million and the hot part will be 1 million plus 300. So you see my point right here? This ratio is crazily very close to 1 right there. And that means this ratio will be very, very close to 0. So it means you almost get nothing out of it. But on the other extreme, if I'm looking at, if you're trying to run the machine between 1 Kelvin and 301 Kelvin, see, that's also 300 Kelvin apart. So your efficiency will be 1 over 301. Whoa, this is going to be very, very close to 1. It's very close. Actually, it would be nice if you can run between 0 and 300K. Is that right?
Okay.
If that is the case, then it's going to be 1 minus 0, and you're going to get 100% efficiency. But we already discussed this is not possible because the 0K is an unattainable temperature. So this is the linkage between what we are studying in terms of the efficiency back to what we are trying to say, that there's no engine in this universe that can run 100% efficiency. That means there's no engine in this universe that can draw energy from the hot reservoir and turn it into a useful work 100%. All right. Wow. Got that one? So by looking at the expression of the Kernel engine and the Kernel efficiency here, that can link you back to the only possibility for you to get 100% efficient engine running is by having the Q core or the T core to be at 0K. Got that one?
Okay.
All right. So that's what it means by this give you the limit, upper limit of the efficiency that is possible. And in reality, you know, you cannot build a Kernel engine. That's not possible. The actual engine will look something else. So if I'm going to use these concepts to build like a USB device and use it to charge my smartphone, let's say my body temperature, T body, let's say is about like 37 and all this stuff. So let's say it's about 310 Kelvin. And let's say room temperature is at about, well, 25%. So let's call it like, well, 290K, the room temperature. So that means between my body temperature and the room temperature, of course, my body will sort of dissipate heat all the time. Yeah, that's what it is. But to extract the heat from my body heat and turn it into some, USB signal and other stuff, my upper limit of efficiency is going to be my Carnot efficiency. It's going to be 1 minus 290 over 310. So if you punch your calculator, it will run around like one digit number, maybe like 4%. And this is like theoretical. So it means you have to exclude like, frictions, the inefficiency of running some electricity and all this stuff. So there are a lot more stuff that comes into play. So it will dial these numbers down to like super, super close to like, let's say like 1% efficient engine. And that's pretty much useless. All right. So I hope you see what I'm trying to get you to link to something that's useful to think for this theory. All right. And this is also another reason why you cannot build like a electric plant to generate electricity to run a city by using just the temperature difference from the surface of the ocean and the bottom of the ocean. Even though it looks cool, it's like, Ajahn, the top of the ocean is hot, the bottom of the ocean is cold, but now you can see that once the temperature difference is so small, the efficiency of any engine running between those two temperatures are going to be small. It's not going to worth building any machine at all. Okay, makes sense? All right, there's a question comes in. So if heat can't be created or destroyed, where does the atoms get their minimal heat energy? Just from existing. All right, I think your question is deeper than thermodynamics. So I'm just going to have to answer this after the class. Sounds good? All right. Yeah, that is something related to, I'm going to have to say, once you're down to atoms, atomic scale, it's going to be quantum mechanics come into play. And it's from I would say, the nature is not super, 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 super calm. Nature is tickling something, there's something wiggle all the time in this universe. That's what I'm saying. Yeah. So that's why you get something out of blank space from time to time. Well, there was a big bang and other stuff. So there was, I don't know, we still have an unanswered question. All right. So we get back to that. Okay, guys, let's come back to this. We'll keep pushing further these calculations here. You have a Kernel engine takes 2000 joule of heat from a reservoir at 500K. So now the diagram will be useful here. So the engine takes 2000 joule of heat. And now you say the hot reservoir up here is 500K. Now then it discards some heat down to the colder reservoir at 350K. All right. Now the question asks you to find the work done by the engine and the heat discarded. Of course, there was something useful coming out right here. All right. And the straightforward way of doing this is using the Kernel relationship over here. Because you are looking at the Kernel engine, the ratio between the temperature is the same as the ratio between the heat that flow between those reservoirs. That's it. This is the main equation that we can use for the Kernel engine. All right. We know temperature, 350K for the T cold, 500, sorry, 500 for the T hot. The Q hot is known to be 2000 joules. So from here, you can, thank you, you can calculate Q cold right there. And that's it. It's what? 14,000 joule. Is that right? Oh, is that 1400? I think 1400. Sorry. That's not gonna be nice. You draw in 2000 and then you get 14,000. All right. Okay, so that's what it is. That's 1400. Get discarded right here. And that's answer pretty much everything. So the work done It's just a difference between the two. You pull in 2000 joules of heat and discard 1400. So the work done is going to be 600 joules. Sounds good. And from this, you can even calculate the efficiency if you like. It's going to be what you get, that's 600 joules, divided by what you have to provide, and that is the 2000 joules of heat from the hot reservoir. And that's it. Your engine is running at, what's that, 0.3? Or is it 30% efficient? It is 30% efficiency. Very good. All right, so I think you get the idea of the efficiency, the upper limit that's being capped by the Kernel efficiency. All right, now it's getting more complicated. Let's pull everything all together after 5 lectures and a half. Now is your time. We're gonna start dragging everything, the equation of states from the gas, PV diagram, all the processes, the way that you calculate the heat, the work, the change in the internal energy, combined with the efficiency of the heat engine. You have now a cyclic process in the PV diagram. Answer the following questions. All right, guys, this is the moment. All right, so this is it. You have a heat engine operates using the cycle shown. It has to be a cycle because your engine is supposed to run and run and run, in cycle. The working substance is 2 moles of helium gas. So we can assume that the helium gas is monatomic gas. So which reaches a maximum temperature of 327 Celsius. So let's get rid of this first, guys. Convert it into Kelvin. And that just add 273. So that is going to give you 600 Kelvin. All right, that's there. So that at least they say reaches a maximum temperature. So at least now you know it's supposed to be the highest point in the PV diagram. You guys with me? Because everyone knows now in the PV diagram, the higher the point, the higher the isotherm underneath it, the higher the temperature that is going to lie. So that's what it is. So assume the helium gas can be treated as an ideal gas. It has to be. We have no other ways to do it. Process BC is isothermal. That's good news. That is very good. So that's, let me highlight this. So this is an isothermal. So BC is isothermal. So that means the BC process must be lying on an isotherm. And because that is the highest lying points in this PV diagram, that indicates that this line is going to be 600 Kelvin isothermal lines. Okay?
Okay.
Got that one? Okay, just let me know if you sort of like do not follow at any part, but that's what it is. Okay, now the pressure in state A and C is 10 to the 5th Pascal. A and C are at same pressure, so that's good. Let me draw the information in there, 10 to the 5th. And the pressure at B is also given to be 3 times that. So 3 times 10 to the 5th. Now, let's answer these following questions. How much heat enters and leaves the gas each cycle?
Okay.
Go ahead, guys. It is your turn. Let's try answering this first question. Let's see if everything that you have learned in the past 5 lectures can answer this first part. Part A. How much heat enters and leaves the gas each cycle? They want to know the entering heat and exiting heat. So do you have to calculate pretty much everything? Do I have space? Oh, I have some more space in the next page. So this is good. All right, let's answer part A first, guys. All right, it's going to be a long computation from now on because, I mean, you will be able to answer everything. So that's why it takes many calculations to reach each individual questions. It takes, I mean, it's like doing accounting. Okay, guys, part A. What do you think? So of course we have to break down into sections, right? There are some 3 segments in here, A to B, B to C, and C to A. So we have to do them separately. So we start from A to B first. So part A, let's go from A to B, shall we? Now, A to B is constant volume process. First thing first, no work done. From the first law of thermodynamics, delta U equal to Q minus W, W is gone. Okay, and you know the change of the U can be calculated as 3/2 NR delta T. A quick reminder, we had one special treatment for this one, and we name it the specific heat in the constant volume process. All right, but as you can see, you don't need to know this if you don't want to, but you're going to arrive to this expression anyway at the end. So the only question that you have is just calculating this. Is 3/2 N is known to be 2 moles. No big deal. R is R. I just love to keep it as R. Now the delta T is going to be T at B minus T at A. T at B is already known to be 600 K. So the only thing left for you to calculate is, can you figure out the temperature at A? Well, that's no big deal. That is just the states of the gas. So what I can do is PME over TA equal to BB over TB. Yeah. Okay.
Okay.
And with that, because A and B are at the same volume, the volume cancel. And because the pressure at A is 3 times the pressure at, the pressure at B is 3 times the pressure at A. So the temperature at B is going to be 3 times the temperature at A as well. Yeah. So just to be clear, this is what we have been doing all along. So point A itself must be on another isotherm, correct? Yes. And that, now we know it's 200 K. 3 times lower. Then that's it. Come back here, 2 cancel, 3 R times the change of the temperature. Final temperature is 600, initial temperature is 200. And then at the end, you're going to get 12,000 R. That's it in joule. Done.
Okay.
Is my number correct? Yeah, 12,000 R. Okay. And that is positive. Remember that when we do this, everything perfectly in order, the sign at the end is automatic. So having the sign at the end to be positive, it means the heat flow into the system. Into the system. So this is, the arrow is for. Let me call this QAB. That is the heat flow during the AB segments. And that is going to be the same thing as the change in the internal energy during the AB segment. And that is first part.
Okay.
Got that? See, not too bad, but it takes quite a little bit of calculations to get through to the end. Try again, guys. Give me heat from B to C. So everyone still follow, yeah? All right, just let me know if you sort of, or I'm missing something, all right? Just let me know. All right, B to C, guys, come on. Just kidding. I mean, what the is like thinking? It's like thinking or what? B to C. So first thing first, what kind of process is this? Yeah, it's already said. It's an isothermal process. So from B to C, definitely delta U is 0. U is unchanged. Okay.
Okay.
First law of thermodynamics goes delta U equal to Q minus W. Delta U is gone. So this lead to heat is just work. And you have done this a couple of times because it's the area under the curve. We got this curve from integrations. And this one is, if you remember, nRT log V final, which is at point C, over V initial is V at point B. You guys with me? Pretty good.
Okay.
Not bad. So that means I can just plug it in right away. N is 2, R is just R. T is temperature at B or C. They are lying at the same temperature. So I can pick a point. I can pick T at B, and that is known to be 600 K. And now all I have to do is just take the log of the final volume and the initial volume. Once again, that's not too hard to do because you just take the ratio, correct? And it just come as, again, PB over TB equal to PCVC over TC. Yeah. All right. And then because in this segment over here, temperature are exactly the same. So the products between the pressure and volume stay fixed. But now you can guess. You don't have to guess. You can calculate.
Okay.
You can calculate because pressure at C is 3 times lower than the pressure at B. So that means the volume at C must expand 3 times to compensate for that. Yeah. All right. So that's good. So the volume at C supposed to be 3 times of the volume at A. So that's log 3. Cool. And that's it. Make it a little bit nice and clean. So this one is it's going to be 1200 log 3R joule. Okay.
Okay.
And once again, as you can see, the numbers that you got over here is positive. So this one means the work done is positive and the heat is positive, right? The work done is definitely has to be positive. It's confirmed because gas is expanding. It has to be a positive work done by the gas. And the heat has the same sign as a W in this case. So the heat is also positive, means the heat flow into the system, guys. Woohoo. All right, so let me move this away a bit. Right there. All right, so heat is in QBC. Isn't that cool?
Okay.
I don't know if it's cool or not, but everyone is quiet at this point, so I'm just keep going. All right, guys, C back to A. Your turn. Just kidding. All right. C to A. Now is an isobaric process, correct? Very good. This is the process that you retain all 3 parameters because you have delta U non-zero. There's a work done definitely because there's an area under the curve. And that must be heat. Heat is there all the time. Okay, very good. So let's attack the first one. For the isobaric, you should be able to calculate the work done during this process. Is right here. Okay, so let me do like a straightforward way first. Okay, I'm just gonna start from the work done. Okay, so the W is just gonna be P delta V. You guys with me? It's just the height times the width, P delta V. And then you plug this into the delta U equal to Q minus W. So the heat is going to be delta U plus W. Start to ring any bells right here? The delta U always 3/2 NR delta T. The W is just P delta V, but the P delta V is once again is just NR delta T. So I can say it's 3/2 NR delta T plus NR delta T. And then you end up with the 5/2 NR delta T.
Okay.
Remember this, right? Because we already discussed a couple of times that in the constant pressure process, you can jump right into the heat during the constant pressure process to be 5/2 NR delta T. And we even rephrase this one as a NC sub PD delta T. Very good. So as I told you, you don't need to memorize the formula if you don't need to. You can start everything right from the definition of each single terms in the first law of thermodynamics. You get back the same results. But of course, if you do it multiple times and you're familiar with this, comfortable with this, you can say about Ajahn, let's jump right into it. The heat flow from C to A during CS segments is going to be 5/2 N R delta T is going to be T final minus T initial. You guys with me? Yeah, jump right into it. Why not? And we know temperature already. Final temperature is 200. Initial temperature at sea is 600. So this is good. So 2 cancel. So it's going to be 5 or, here we go, negative 400 K. Negative 400. Because final minus initial, final temperature is lower than the initial temperature. So you get negative 400 there. And at the end, let me squeeze in here. It's a negative 2000 R. See, the sign is automatic. You get the negative heat from C to A. So it means heat leaves the system here. Let me put the arrow outward right there. Q, C, A. And that completes the whole thing, guys. That's it. I'll start talking right now because it's just part A. We haven't gone that far. All right, but anyway, we get all of the information right now. That so you can answer now. How much heat enter? All right. So to the enter of the heat is gonna be these two. Okay, let me highlight. The entering of the heat is gonna be this and this. That is enters. Okay, and leaves is gonna be down here, right there. So let me mark on this one. So the heat enter is gonna be QAB plus QBC. And the heat leaves is QCA, right there. Perfect. So as you can see, just only one line of questions, it takes a lot of calculations. Too bad. That's how thermodynamics works. It seems like it's a different kind of calculations to me. It doesn't look like mechanics or anything. All right, part B, guys. How much work does the engine do each cycle? And eventually you should be able to get to the efficiency. Okay, let's think about this for a couple minutes, guys. Part B. We have the next page, but I think all the information is right here. How can we answer part B? How much work does the engine do each cycle? And what is its efficiency? What do you think? It's too quiet. Oh, this is not a good sound effect right there. That's not good. That's gotta be me. Sum up the cycle. Pretty close. Oh, actually, that is true. If you take into account the sign, yeah, you sum up the cycle. Correct. Okay. So I want to show you this. Can you compare this with the diagram that we have been talking about in the heat engine? Can you see that? There is a heat that flow in and there's a heat that flow out. So if I compare this with the diagram, so that means, okay, so let me sort of shrink this thing down, keep it somewhere. Yeah, look at this. There is an engine. Okay, so that means the heat that flow in is a QAB and a QBC, and the heat discarded down is a QCA. So the only thing left for you is just to, Ajahn, just take the difference. The in subtract the out must be equal to the work done. But then your friend said correctly, because we already taken into account the sign. So if you take in the sign, all you need to do is just sum them up, because the incoming heat will be positive and then outgoing heat will be negative. So when you sum them up, the rest will be W. So let's do that. So part B, the net work done is going to be, so if I put the absolute sign here, it's going to be QAB, that's in. So I take the positive one. BC segment, that's also in. And then I just subtract out the QCA because I know that is the discarded heat. You guys with me? All right. And just to confirm your friend's point, is just exactly the same as summing them all. Same thing. Okay, but taking the sign along with it. Okay, and all you have is just like plug in the numbers 1200 R for the AB, and then you have 1200 log 3 R for the BC, and then you subtract out or you add that negative 2000 R in it. And that's the work done, guys, for this cycle right here. And if you really do your calculation using calculus or whatever, if you want to find the area under the curve, we already agree on this. Every time that you have a closed cycles like this, a cyclic process, the amount of work done that you have over here is going to be the same thing as the area enclosed by that cycle.
Okay.
All right. And if it's going clockwise like this, the net work done is going to be positive all the time.
Okay.
And that's already verified by this number right here. Okay. And what about efficiency? All right. Very good. So, that's the answer comes in very nice. So efficiency, all you need is it's a Q hot, right? Over Q cold. But the key of the hot and the cold is more like the in subtract by the out. So that's the purpose of this one. The in is this 2 heat right here. And the out is this dude right there. Okay, so the efficiency is what you get over what you have to provide. What you get right now is this W, you just calculated it. So at the end, now you have all the information that you want to do. So it's going to be the W. Now let's use blue for that. Yeah, that's what you get over what you have to provide, which is the incoming heat. That's it, guys. With me? The work done that you just calculated, you can plug it in here, and then you divide it by the heat that you have to draw in to your system. And of course, you can play around with this ratio because then you know that the W is just a difference between the Q in and Q out. So right, all the numbers are there for you to manipulate. Cool.
Okay.
All right. And let's move on to the part C. Compare this engine's efficiency with the maximum possible efficiency attainable with the hot and cold reservoir used by this cycle. So the good thing about this one is actually you can calculate this number exactly, right? Because we know all the numbers already. So let me try showing you this. From the numbers that we got, okay, even though we have R all over the place, but now you start seeing that what you're getting over here is going to be this number right here. And you can start seeing that now all the R cancel. You don't need all the R's. All right, so if you calculate this ratio right here, that will be the efficiency of this particular cycle. But then you want to compare this number to the numbers if this were to be a Kernel engine instead of this like sort of curved triangle shaped stuff. So part C, the efficiency of the Kernel is going to be 1 minus T cold over T hot. So all you have to look for is in this cycle, where is your coldest part and where is your hottest part? The coldest part is at point A and it's sitting at 200 Kelvin. The hottest part is either B or C, and that is at 600 K. So that means it's going to be 2/3 efficiency, or you can say it's about like 66.67%. All right. Looks cool. Already. And that means the numbers that you're going to get from part B, this not going to be able to compete with 66.67%. Oh, somebody got me the different number. 0.206. All right, you guys, check my work. Did I do something wrong here? No, but efficiency is so easy. It's 200 over 600. So I'm sure the efficiency will be 2/3. That's going to be 2/3. Thank you. Oh, for part B. Thank you very much. And that is 0.206. And this one is 0.067, let's say. Yeah. So as you can see, the given process is not very efficient at all. It's only like 20% efficient. But if you replaced this engine with a Kernel engine, then you get up to 66%. All right, got that one?
Okay.
Okay, and now you start seeing that I think that's the ultimate questions that you're going to face in the exam is like this. If I'm asking this, it's pretty much you have to calculate everything.
Okay.
Right? I mean, you have to do the work, the Q, the delta U, the efficiency, I mean, everything that you have learned is in here. All right, but I think you see the whole point. Okay, let's do one more, shall we? And that's it. That's just gonna be pretty much the last exercise of the day. And then I think next time on Wednesday we can wrap things up. And I think it's a good point to well, we can, I mean, if we can use this one on Wednesday as well, actually, that's kind of nice. Okay, because we have another lecture to go through. So actually, okay, why don't we do this? Because I don't think I can finish this one in 5 minutes. That's not possible. And it might take like 15 or 20 minutes to explain and go through. And I think it's a good point. Why don't you guys take this home and then, well, you're already at home. Why don't you take this exercise and try to do this one yourself and see the results? And we can match and compare notes and stuff on Wednesday. Sounds like a good plan?
Okay.
All right. And then on Wednesday, I think it's going to be the last lecture in this module right here about the thermodynamics. So I think next on Wednesday, I think we can discuss about when you would like to take the exam on this module as well. Or you want to discuss now if you want. All right. When you want to take the exam on this one, right? I think you can set the date because we can do off timetable and everything. So we can do at any time. And as we already discussed and agrees that we're going to do the like a take home, like sort of like all day take home or something, all night, more like all day. Yeah. All right. Oh, okay. Or another way, if you guys don't want to do it now, why don't we just like, you can comment on the line group if you like, so we can discuss. And because I think there are maybe 5 people missing from today's lecture. So why don't we maybe just post something in the line group and then we can start discussing that. What's the date? All right. It can be Saturday, Sunday, whenever you like, anytime. All right. Because it's a take home anyway. So, all right. And from the plan, it's like, I'm going to release the exam in the morning and collect them in the evening, something like that. You might have like 12 hours to do something like that. Okay, cool. All right. So sounds like a plan. Okay. So let's, if in the meantime, from today to Wednesday, if there are anything that, I mean, if there's anything that you want to add to it, you can use the line group to communicate and we can draw the final conclusion on Wednesday about the exam. Sounds good? All righty. Okay. So don't forget to try this exercise, guys. It's a very good one. It looks like an exam question, actually. All right, guys. And take care of yourself. And I'll see you guys on Wednesday. Yeah. Okay. Bye-bye.